Hi, my name is Luis de la Rosa. I am a fourth grade teacher and I love math. I'm going to model a lesson where we are going to connect fractions, divisions, and clocks. And speaking of clock, have you noticed that our clocks are based on the number 60 seconds in a minute or 60 minutes in an hour? The question is, why don't we use the number 10 or the number 100 since our number system is decimal, is based on the number 10? Well, actually it has to be with the ancient Sumerians, a group of people who lived thousands of years ago in what is now Iraq. They were the first known civilization on Earth, and they were very smart, and for some reason they loved the number 60. Let's see why. I drew 1, 2, 3, 4, 5, 6 different clocks, and I started partitioning in different equal parts. The first is easy. 60 divided by 2 is 30, because 2 times 30 is 60 minutes. So 1/2 plus 1/2 is the whole, the complete, the total. Can I divide 60 by 3? Yes, it's 20 minutes. 20 minutes. So I know that between two consecutive numbers on the clock there are 5, so is 20 would be 4 times 5. So it would be here where the 4 is, and then 4 more 8, and 4 more 12, because we also know that if we go around the clock, there will be 12 hours. So 1/3 plus 1/3, 3/3 is 1 hour. What about 4? Can I divide 60 by 4? Sure. And we have the quarters. And everyone knows that every quarter is 15 minutes. So 15 times 4, or 4 times 15, because of the commutative property, we have 60. So 60 divided by 4 is 15 minutes. What about 5? Well, if we know our multiplication facts up to 12, we know that 12 times 5 or 5 times 12 is 60. So I start from 0 plus 12. 12 is more or less here, a little more than 10, plus 12, 24. 1 minute before 25 here, plus 12, 36, 1 minute after 7, plus 12, 48, 3 minutes more than the 9, which is 45, and then 60. So 1/5, 1/5, 1/5, 1/5, and 1/5. Of course, I can divide 60 divided by 6 is 10, because 10 times 6 or 6 times 10 is 60 minutes. I have 6. 6 times 1, 6. And if I reverse this division, 60 divided by 10 will be 6. So if I put 6 minutes here, 6 minutes is 1 minute more than 5. 6 minutes, that would be 1/10. And 10 times this little portion will be the whole hour. What would happen if instead of having a clock of 60 minutes, we use a clock of 10 minutes? Let's see how it would work. So I did that. This is a repetition of what I did, and now we have the new clocks. 100 minutes, 100 minutes. Again, this little apostrophe here means minute. 100, 100, 100, 100. I can divide 100 by 2, and I get 50. So 1/2 is 50. It's funny because 1/2 here, 1/2 here, but here is 30 minutes, here is 50, because the total is different. Now we have a total of 100 minutes in our fictional hour. Can I divide 100 by 3? Well, I can, but it's not going to be clean, because we know that 3 times 30 is 90, so it would be a little more than 30. 35 would be 35 plus 35, 70 plus 35, 105. That's too much, so it's between 30 and 35. Actually, 33.3333, and this is a decimal number. This is the tens place, the unit place, the decimal point, and the decimal digit. If I add this number 3 times, I get 99.9999999 infinite times, which basically is 100. Besides, you can see I wrote the word no, because this is not convenient at all. 33.333 is not an easy number to deal with. Can I divide 100 by 4? Sure. Remember the dollar. The connection with the dollar. A dollar has 100 cents. I have 4 quarters. Every quarter is 25 cents. So 4 times 25 or 25 times 4 is 100. 100 divided by 4 is 25. I can divide by 5, and 1/5 would be 20. Why? Because 5 times 20 or 20 times 5, according to the commutative property, would be 100. 100 divided by 5 is 20. With a 6, I have the same problem with a 3. Because why? Because 6 is 2 times 3. 2 works, but 3 doesn't work. So it's expected that 6 is not going to work. If I do the long division, 100 divided by 6, I start with 10, 1, I get 16.66666 infinite times. Again, this is not a number of minutes that is easy to deal with, so it's not convenient. And I can divide 100 by 10, and 1/10 would be 10 minutes. But I am missing the cleanliness and the simple number of minutes for 1/3 and for 1/6. Maybe 60 is better than 100 because of this. This look like upside down trees. We say we are factorizing the number 60 and the number 100. 60, but 2 times 30, 60. I cannot decompose 2 more, like 2 times 1, but that's the same number. It's a prime number. I cannot decompose it more. 30 is 6 times 5. 5 again is a prime number. I cannot decompose it more in smaller factors. But 6 is 2 and 3. If I circle the tips, the ends of each branch, I have 2 plus 2 plus 3 plus 5, which is 60. But look at this, I have 3 factors. I have 2, I can divide it by 2, I can divide it by 3. 2 times 2 is 4. I have 5 here, 2 times 3 is 6. And then I have to jump to 10, 2 times 5. What happens when I factorize the number 100? I know that 2 times 50 is 100. 2 again is prime. 50 is 2 times 25. 2 is prime. I keep decomposing 25 into 5 times 5. So it's 2 times 2 times 5 times 5. So instead of having 3 different factors, in the case of 60, I have only 2 and 5, and they are repeated. And I can see here, I can divide it by 2. There is no 3. That's why the division by 3 wasn't really clean. 2 times 2 is 4. 5. 2 times 5 is 10. And then, of course, 25 here. But we're only counting up to 10. Maybe that is the reason, this factorization tree, that they chose the number 60 over 100. I would like to invite you to try other numbers. Like, for example, what would happen with 72, with 84, 24, 36, and 56? Well, if I factorize it, here I have only two factors. 84 has 3, two factors for 36, two factors, two different factors, and there are 4 factors, but only 2 different factors for 56. So the best number in the race for the clock would be maybe 84. I have 2, 3, and 7. 84 is using the ends of the factorization, the end on the branches. I have 2 times 2 times 3 times 7. So I have 2, I have 3, 2 times 2 is 4. There is no 5, that's a failure. 2 times 3 is 6, 7. And I can, because there is no 5, I cannot do 2 times 5, which is 10. I cannot divide it by 10 either. So maybe the best one is 84. Can you imagine a big clock using what number of minutes can I use that I can divide that number by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All the smallest whole numbers. So I would need, look at this. I would need 2, right? Then I would need 3. 4, I can do it 2 times 2. 5 is another prime number, times 5 here. This 2 times 3 is 6. I have 6. I have to put 7, which is another prime number, which means I cannot decompose it in a smaller. I mean, I can put 1 times 7, but I'm repeating the 7. If I want to have 8, 2 times 2 is 4. I have to add another factor, 2. 2 times 2, 4 times 2, 8. And if I want to have 9, I need another 3, because 3 times 3 is 9. So let's check, because in math it's very important to check. It's very easy to make a mistake. You have to look back. Let's see. I can divide it by 2. I can divide it by 3. This is 4. 2 times 2, 5. 2 times 3 is 6. 7. 2 times 2 times 2 is 8. 3 times 3 is 9. And of course 2 times 5 is 10. But what does these 3 numbers is 8. This 2 is 3 times 3, 9. 8 times 9 is 72. And 5 times 7 is 35. So my number is 35 times 72. And you can tell that it's going to be a big number. Look at this. I did it here. You see it here? 72 times 35, 2,520. So my big clock should have 2,520 minutes if I want to divide my big fictional hour by 1, by 2, by 3, by 4, by 5, by 6, by 7, by 8, by 9, and by 10. Of course, nobody wants to have such a long hour. Don't you agree? 2,520 minutes? No.